Okay, so can we start recording it again? So I'll give a quick overview of the different types of study designs in occupational epidemiology. And they're based around this concept of a population, and this is a population followed from birth, but in occupational studies, they would be usually followed from time of first employment. But you can see here a group of people who've maybe been followed for 10 years or so, and they all start quite healthy. We exclude those who already have disease. And this person was followed all the way through and remained healthy. This person got some symptoms of disease, that's the dotted line. This person got some symptoms and then some severe symptoms, so they got severe disease. This person died of whatever the outcome was we were studying. This person died of something else, and this person was lost to follow-up. So most populations we study look something like this. We follow them over time. They get sick, sometimes they die of the disease we're studying, sometimes they die of something else, and sometimes we just lose them. So that's sort of the context in which we're doing these studies. So all epidemiological studies are, or should be, based on a particular population, and there's a lot of different names that people use. So I use the name source population, followed over a particular period of time, which is the risk period. And the different study designs differ only in how the source population is defined and how information is drawn from this population and time period. So the main theme of this talk is that you hear about cohort studies, case control studies and so on. They're all really trying to do the same thing, just in different ways. So they're different, but they're not completely different the way that they're sometimes taught. There's very clear relationships between the different study designs. Now, when we study people over time, incidence is the number of new cases of the disease over a specified period of time, and prevalence is the number of cases at a particular point in time. So if we look back here, let's say we're studying something like asthma symptoms, and when the dotted line starts, then the person has developed symptoms. So there's 1, 2, 3, 4, 5 people developed the disease during this follow-up period. So the incidence is essentially 5 out of 10. It's a bit more complicated than that, but for starters, that's a reasonable estimate. On the other hand, if we look at one particular point in time, like here, you can see there's, at this point in time, if we draw a vertical line, there's one person who has the disease at that particular point in time. So incidence is about occurrence of new cases over time. Prevalence is just one point in time, and it's the proportion of people who have the disease at that time. The slides at the end have, I've got some slides on prevalence, but I'm just going to focus on incidence in this talk. So incidence studies are known as also known as cohort studies, follow-up studies, longitudinal studies, prospective studies. They use all the information on the source population and risk period. So you basically include everyone and you follow everyone for the whole length of time that's available. And we compare the incidence in the exposed and non-exposed groups. So here's an example of incidence study. We maybe follow 1,246 babies born in Tucson, and they collect a lot of exposure information at birth, and then they follow them over time and see who gets, in this study, wheezing, essentially asthma-like wheezing. So here's some hypothetical incidence data. We have 10,000 exposed people and 10,000 non-exposed people. And let's say we follow them for about 10 years and we see who gets the disease that we're studying. It doesn't really matter what it is. And you can see in the exposed group, over 10 years, 1813 out of 10,000 get the disease. And that's an incidence proportion of 0.1813. So it's just 1813 over 10,000. There's lots of other words that people use for this. It's some people call it cumulative incidence. Risk is the easiest term. So it's your risk of getting the disease over the next 10 years. And in the exposed group, it's essentially 0.18, so it's 18%. In the non-exposed group, it's 952 over 10,000, so it's 0.0952, which is about 9.5%. And the risk ratio, 0.1813 over 0.0952, is 1.9. So the exposed group, the proportion that get the disease over the risk period is about double in the exposed group compared to the non-exposed group. Now, this looks simple, but there's some big problems with calculating these numbers. And the problem is essentially the people who get lost to follow-up. So if you look back here, let me just fix this. If you look back here and see how many new cases of the disease there was 1, 2, 3, 4, 5. But it's not really 5 out of 10 because you started with 10 people, but not all of them were followed right to the end. Some of them were lost to follow-up, and some of them were died of something else and were therefore lost to follow-up. So you can't really say that 5 out of 10 people got the disease over the 10 years because some of them we don't know what happened. We don't, we only followed them for a few years. Now, if you followed everyone right to the end, like if we followed people for 150 years, then, and suppose we were studying death from any cause, then what would be the risk of death in the exposed group? Well, it would be 10,000 out of 10,000 because we all die once. And in the non-exposed group, it would be 10,000 out of 10,000. So in fact, the risk ratio, if you follow people long enough, goes down to 1 because everyone dies once. There's 100% mortality in the exposed group and 100% in the non-exposed group. So these are the problems of calculating risk. It's the proportion of study participants who experience the outcome for the first time. If they already have the disease at the beginning, we exclude them. But when there are significant losses to follow-up, the risk cannot be estimated directly. And there's this additional problem that if you follow the population long enough, then essentially everyone's going to die and experience the outcome in some form or another. So the risk is a really useful concept, but it's actually quite hard to calculate because of this problem of loss to follow-up. So what we actually need to do is count how long we follow people for. So I'll just go back again. So this person was followed for about 3 years and then they got the disease. This person was followed for 10 years. This person maybe 5 years, then they got the disease. This person maybe 4 years. This person maybe 3. This person maybe 8 years, 4 years, 6 years, 2 or 3 years. So what you need to do is for each individual, add up how long they were followed for before they either got the outcome we were studying or were lost to follow-up because they got lost or they died of something else. So if we go back to this previous table, we can calculate the incidence. And there's 10,000 exposed people followed over 10 years. So the maximum number of person years of follow-up we could have is 100,000, 10 times 10,000. But of course, not everyone's followed for the whole 10 years. And also once you get the disease, then they stop counting you from then on because you're no longer at risk. You've already got it. So roughly, if you had 10,000 people followed for 10 years, in this instance, you would have about 90,000 person years of follow-up. And as before, you have 1,813 cases divided by 90,000 person years of follow-up. So that's an incidence rate of 0.02. And the units don't really matter. What this says is that for every 100 people, 2 of them, for every 100 person years, there were 2 cases of disease. For every 1,000 person years, there were 20 cases of disease. For every 10,000, there were 200 cases of disease. The units don't really matter. It's just like if I'm driving along, you can say I'm doing 50 miles an hour or 80 kilometers an hour. They're the same thing, they're just different units. And the main thing is that we use the same units for the exposed group and the non-exposed group. And in this hypothetical example, the incidence rate is 0.02 in the exposed group, it's 0.01 in the non-exposed group, and the rate ratio is 2. So that's the second thing we can calculate in a cohort study. It's the number of new cases per unit time. And this is something we can calculate just by counting up the cases and counting up the person years. And there's a formula we can use to use the incidence rate to estimate what the risk would have been if everyone had been followed for the whole 10 years and not lost to follow-up. So in fact, when they say, for example, that if you have a certain blood pressure and age, that your cardiovascular risk for the next 10 years is 20%, maybe, we can't actually estimate that directly from studies. The way they've got that figure is by working out the incidence rate and then using a formula to see what the corresponding risk or proportional incidence is. Now, there's a third thing we can estimate in a cohort study, which is the odds. And so the risk was the cases divided by the total number of people. The odds is the cases divided by the non-cases. So it's the number of people who got the disease sometimes during follow-up divided by the number of people who were followed to the end and didn't get the disease. So here the odds is 1813 over 8187, which is 0.22. And in the non-exposed, it's 952 over 9048, which is 0.1052. And the odds ratio is 2.1. So the odds is the ratio of the number of people who experience the outcome to the number of people who don't experience the outcome. It has the same problems as the risk, that if you lose people to follow up, you actually can't estimate it directly. And it also has some unfortunate statistical properties, which means we don't actually use it in cohort studies anymore. But I just mention it here because it is the third outcome measure that in theory you could calculate, and it relates to case control studies. Okay, so those are the three main measures we can estimate in a cohort study: the risk ratio, the rate ratio, or the odds ratio. And they all have the same numerator. There's always the number of cases on top is always the same. The risk is cases, 1813 divided by the total number of people you start with. So 1813 over 10,000 is a risk of 0.1813. The rate is the cases divided by the person years, and that gives you an incidence rate of 0.02. And the odds is the cases divided by those who never get the disease, 1813 over 8187, which is 0.22. And this gives us the risk ratio, the rate ratio, and the odds ratio. And you can see they're all pretty similar. They're all about 2, so it's about double in the exposed group compared to the non-exposed group. And I've deliberately made this, so this is a very common disease. 18% of the exposed group got the disease over the 10 years of follow-up. If it was a very rare disease, then they would be very close together. They might be 2.00, 1.99, 2.01. So if the disease is rare, they're basically identical. If the disease is common, then there is a difference between them, but the difference isn't very big. The only one we can estimate directly is the incidence rate and the rate ratio. The risk and the odds, if we estimate the rate, there's formulas we can use to estimate what the risk would be if we had managed to follow everyone for the whole period of time. And in theory, you could also work out what the odds is, though there's no reason to do that. So I'll just stop for a moment there. This is very generic, but in the subsequent lectures, you'll have a lecture on cohort studies, you'll have lectures on case control studies, both by Michelle, and they'll go into a lot more detail. So here we're just giving a very quick overview. But before I carry on, that's all I'm going to say about cohort studies at this stage. is there any quick questions you've got about cohort studies before I then go on to talk about case control studies? Everyone's blanked out, so either they have no questions, or they've actually gone to get a cup of tea or coffee. Okay, I'll assume that that's okay, and I'll carry on with talking about case control studies. Sorry, I've just got a little bit lost here. Okay. So that summarizes what we can do in terms of what we can estimate in a cohort study. There's three things we can estimate. We can estimate the risk, or the rate, or the odds of the outcome. And the numerator, the top line, is always the same, but the denominator differs. So that's what gives us the three different measures. Okay. So let's go back to this, the example of the odds. In the exposed group, we had 1813 cases and 8187 people who never became a case. So the odds was 0.22. In the non-exposed group, we had 952 cases and 9048 people who never became a case. So the odds is 0.1052. And the total number of cases is 2765, and the total number of people who never get the disease is 17235. So if we look at the odds ratio, it's 1813 over 8187 divided by 952 over 9048. So that's the top line here. And in some textbooks, you'll see these labeled as A, B, C, and D. So it's A over C divided by B over D, which is just AD over BC, if you remember algebra from high school. Okay, so that's the standard formula for the odds ratio. In the bottom half of this slide, I've just rearranged the formula, and it's exactly the same. You can try it on your calculator or on your phone and verify that it's the same thing. So 1813 over 952, that's the new top line, divided by 8187 over 9048. So that's A over B divided by C over D, which is once again just AD over BC. So why have I rearranged it this way? Well, what you see now is that the top line is the cases. They're the people who got the disease. There's 1813 cases in the exposed group and 952 cases in the non-exposed group. And the bottom line is those who never got the disease. And there's a lot more of those. So if you go back here, you can see there's 2765 cases and 17,000 people who don't get the disease. And the odds of exposure in the cases is 1813 over 952. The odds of exposure in the non-cases is 8187 over 9,000. Now, whatever study we do, we would almost always want to keep all the cases because there's not so many of them. So to estimate this proportion of exposed and non-exposed, we need to as many people as possible. And this is a very common disease, but if there was only 200 cases, then that number is very small, and we would definitely want to include all of them in the analysis. But do we really need to include 17,000 non-cases just to estimate the proportion of non-cases of the ratio of exposed to non-exposed? What we can do is actually study all of the cases and take a sample of everyone who didn't become a case. So we study all of the cases and we take a sample of controls from those who never became a case. And that's all a case control study is. You're studying all of the top line, all of the cases, and a sample of those who don't have the disease or don't get it during the follow-up period. And how many controls would you choose? Well, there's 2765 cases. So as a starting point, it's reasonable to choose 2765 controls out of these 17,000 people. And if we take a good sample, on the average, the proportion who are exposed will be the same as the proportion in this population we're sampling from. So it's slightly less than half, slightly more than half. We choose 2765 controls, and on the average, if we take an unbiased sample, slightly less than half will be exposed and slightly more than half will not be exposed. So we can estimate the odds ratio by taking all of the cases and a control sample of the non-cases. So these are your cases again. That hasn't changed. We include all of those. And we've taken a sample of 2,765 controls sampled at random from the people who never got the disease. And on the average, the proportion who are exposed will be the same as the population we're sampling from. So now back here we have a cohort study, and we calculate the odds in the exposed and the odds in the non-exposed, and we get the odds ratio. Here we're doing a case control study, and we include all the cases and look at the odds of exposure, and a sample of controls and look at the odds of exposure, and we calculate the odds ratio. And it's actually symmetrical. It doesn't matter which way round you do it. You can have A over C divided by B over D, and you'll get 2.11. Or you can have A over B divided by C over D, and you'll get 2.11. So on the average, the odds ratio you get from the case control study will be exactly the same as the corresponding odds ratio you would have got if you'd done the cohort study and studied everyone. So this case control study yields the same estimate as would have been obtained by a full cohort study, but with a much smaller number of participants, because we include all of the cases, but only a sample of the non-cases. And the advantage of this, of course, is that firstly, it's a lot cheaper. Here, for example, we're studying 2,765 plus 2,765, so it's about 5,000 or 6,000 instead of 20,000. But if the disease was very rare and we only had 200 cases and we had maybe 200 or 400 controls, then it's much smaller. You're only studying a few hundred people instead of 20,000. And it's a lot cheaper. It takes less time usually, particularly if it involves interviews. Maybe if you're having to do blood tests and do genetic testing or something, then it's much cheaper because it's a much smaller number of people. And also because it's a smaller number of people, you probably have more time and funding to get much more detailed information on them. So you can actually do a better study because you can get more detailed information. One qualification to what I've just said, what I've just shown you is the way that case control studies are taught traditionally, that you find all the cases and you find the people who never become a case, and they're the non-cases, and you sample controls from those. And that's called cumulative sampling, and it corresponds to sampling from the denominator for the odds ratio if you've done the full cohort study. But if you think back to my slides on a cohort study, there were 3 ways to estimate the outcome in a cohort study. And it turns out there's 3 corresponding ways that you can sample controls in a case control study. And I won't go into them in this lecture, but you just need to be aware of them. They're called cumulative sampling, which is what I've just shown to you, case cohort sampling, and density sampling. And in fact, density sampling is the preferable method and the one we most commonly use, but case control studies are most commonly taught the way I've just shown, where you're sampling the controls from those who never get the disease. So the methods of sampling controls, you can do it from the survivors, those who never become a case. You can do it from the source population, that is everyone you started with, or you can essentially sample from the person years. And they will essentially give you the same answers as you would have got if you'd done the whole cohort study. If you sample controls from those who never become a case, which is what I've just shown you, the odds ratio in the case control study will estimate the odds ratio, corresponding odds ratio from the full cohort study, 2.11. If you use this thing called case cohort sampling, don't worry about what it is, you just need to know it exists. The odds ratio you get from the case control study will estimate the risk ratio from the corresponding cohort study. And if you estimate from the sample controls from the Pearson years using density sampling, the odds ratio you get from the case control study will estimate the corresponding rate ratio from the cohort study. And this is one reason why there's so much confusion about case control studies, because you get different answers depending on how you sample the controls. And most case control studies are taught the way I've just shown, that you're doing cumulative or exclusive sampling. You're sampling controls from those who never become a case. And in that instance, the odds ratio from the case control study is estimating the corresponding odds ratio from the cohort study. If you do case cohort sampling, the odds ratio from the case control study is estimating the risk ratio from the cohort study. And if you do density sampling, the rate ratio from the case control study is estimated. The odds ratio from the case control study is estimating the corresponding rate ratio from the corresponding cohort study. So there's a lot of confusion about case control studies, because however we do them, we call it an odds ratio, but what it's estimating depends on how the controls were sampled. And here's an example of a typical case control study in, this might be a case control study of lung cancer in London, and maybe we're looking at occupational causes. And typically what we do is we might say, let's look at all the new diagnoses of lung cancer in London during maybe 2010. And so the population of London is very dynamic. People keep coming and going, but the population we're studying is those who are living in London in 2010. And we find all the new cases of lung cancer during that period. And then we sample controls from everyone else who's living in London at that time, who doesn't get lung cancer during that year and doesn't have it already. So we get all the new cases identified through the cancer registry in London, and then we choose controls at random from everyone else living in London at the time. And that's the way most population-based case control studies are done. And it turns out that that actually corresponds to what I've called density sampling. It's essentially sampling from the Pearson years. So the problem is that for case control studies, they're often taught in terms of this idea of exclusive or cumulative sampling. But most times we do it this way. We have dynamic populations and we find all the new cases and we sample from the people in this population at risk at that particular period of time. So most times we teach case control studies this way in introductory courses, but we actually do them this way. When we do them in populations, we are essentially using density sampling and we're estimating the rate ratio. Now, if you didn't understand any of that, that's fine. This is a very quick overview, and these are quite complicated concepts. In other talks in the course, we'll go into case control studies in much more detail. All you really need to know here is that a case control study involves studying all of the cases and a sample of those who don't become a case. But there's different ways you can do that sampling. And the odds ratio you get out of a case control study could be estimating a different thing depending on how the controls were sampled. So misconceptions about case control studies. It's often taught that they go from effect. It's often taught that cohort studies are prospective. You start with the exposure and see who gets the disease. And case control studies, you start with those with the disease and those without the disease, and you look backwards. So they're sometimes called retrospective studies. And therefore, it's argued they go from effect to cause. So there's reverse causality. That they're inherently more prone to bias than cohort studies, and that the odds ratio only approximates the corresponding relative risk from a cohort study if the disease is rare. Now, none of these things are true. In a case control study, all you're doing is you have to define a population in a time period. And then a cohort study, you just follow everyone over that time period. For a case control study, you study all of the cases, the new cases that arise in that population over that time period, and a sample of those who are in that population and time period and don't become a case. They're not inherently more prone to bias than cohort studies. There are a lot of bad case control studies done, often involving questionnaires, like things like diet, where you're asking what someone ate when they were a teenager and they probably don't remember very well. On the other hand, for occupational studies, often we can go back to the work history, the occupational employment records, and we can use essentially the same information that we would have used if we'd done a prospective cohort study. Or if you're doing a genetic test, it really doesn't matter if you're taking a blood test now or you took it 20 years ago, you're going to get the same answer in terms of genetic risk factors. And it's wrong to say that the odds ratio only approximately estimates the corresponding relative risks from the cohort study. If you sample controls the right way, then it will exactly estimate the rate ratio and there's no need for any rare disease assumption. So that's a very quick overview of cohort and case control studies. I do have some slides on prevalence studies, but let's first stop and see if we have any questions on what I've done so far. And if you're confused, and so too confused to ask a question, that's fine. This is a very quick overview. And then in the rest of the course, we will go into these things in more detail. But are there any questions now?
Neil, it looks like there's one question in the chat that asks about how do you relate these differing study designs and results when conducting a meta-analysis?
Well, the thing is, if the disease is rare, then these three outcome measures, the risk ratio, rate ratio, and odds ratio, if the disease is rare, they'll be the same or very similar. So it actually doesn't matter. And we have the generic term relative risk to cover all three of them. If you're dealing with a very common disease, and for example, I do a lot of asthma studies, which is quite common, then that may be an issue. So if you're doing a meta-analysis, you have to, if it's a cohort study, you need to be clear what outcome measure they've used. And if it's a case control study, you have to look at how they've sampled the controls, because in a case control study, they will always call it an odds ratio, but what it's estimating will differ depending on how the controls were chosen. Can we say a few words about matching methods for control selection? I presume you'll say something about that, Michelle, when you talk about case control studies, but very briefly, the example I showed, we chose one control for each case, and that's sort of the default. In some circumstances, it can make sense statistically to choose slightly more than that, like 1.5 per case, but it doesn't make a big difference. The only time it makes a difference is if you have very few cases, like you've only got 100 cases, then, well, suppose you can afford to study 500 people and you've got plenty of cases, then you would probably study 250 cases and 250 controls. If you've got very few cases, like only 100, you might then study 100 cases and 400 controls. So you would have 4-to-1 matching, just because you can get slightly better results statistically just by having more controls, because you can't get any more cases. But going beyond 4-to-1 is usually not worth it. It's a waste of time and money. There's a second thing about matching, like should you match for age and sex and smoking and so on. I'll leave that to Michelle to talk about in the case control session, but mostly we would just, mostly we just match for one or two things like age and sex, and matching for other things is usually at best a waste of time, and it can actually be worse than a waste of time. It can lead to a less efficient study.
So there's one student has her hand up. It's Caitlin.
Oh yeah, hi.
In the US. Hi, Caitlin.
Hi.
Would you like